Hello everyone. In this today's video tutorial, we are going to discuss type 1 of numericals based on fluctuating load. Type 1 will be belonging to the category of completely reverse loading where expected life is of infinity. This type or today's video tutorial is belonging to the course outcome number 3. Investigate and determine fluctuating stress with respect to finite and infinite life of components under simple and combined loading conditions like transmission shafts using modified Goodman criteria. The main idea behind this today's tutorial, video tutorial, is to discuss the method of solving the numericals wherein the applied load and hence induced stress is completely reversed and life expected for the machine part is of infinity. Generally, for the static loads, whenever we design, we are going to equate induced stress with the permissible. In case of completely reverse stresses, as the stress is in form of plus minus sigma, plus minus say 100 Newton, 100 tensile, and in during the half work cycle, 100 compressive, plus 100 to minus 100. Stress, applied load, and hence induced stress keeps on changing from plus to minus, from tensile to compressive, and this work cycle repeats, and therefore being the maximum and minimum stress of same magnitude, therefore average stress or mean stress happens to be equal to 0. And as the mean stress equal to 0, only amplitude of the stress do matter, and that is required to be considered while designing the machine parts subjected to completely reverse stress and wherein expected life is of infinity. For the static case, while designing, we are going to equate induced stress with the permissible stress. And while equating, we are finding out the unknown dimension. To design means to decide the unknown dimensions. In case of static loading, we are equating sigma induced with sigma permissible, wherein sigma induced will have this term, left hand side term of sigma induced will have the unknown dimension, and to the right there is allowable or permissible stress sigma permissible, which will be given by SYT or SUT divided by factor of safety. SYT is the yield point stress. In yield point stress, if the material of the machine part is of ductile nature, then we have to consider, we have to take into account yield point strength. And if the material of the machine part of which the if the material of the machine part is of brittle nature, then we have to take into account SUT, ultimate tensile strength. So therefore, based on the nature of the material, we have to take into account either of SYT or SUT, and that divided by factor of safety will represent allowable or permissible stress, which is considered on right hand side of the equation. This equation is assumed to be universal equation of designing. Any design can be completed, any design can be formulated using this only equation wherein induced stress is equated with permissible. This is the only equation which covers any kind of design, any kind of machine design, mechanical design. Therefore, many times it is referred as universal design equation. So, universal design equation for static loading is sigma induced is equal to sigma permissible, wherein sigma induced is given by SYT or sigma permissible is given by SYT or SUT divided by factor of safety, and to the left hand side there is sigma induced wherein unknown dimension will be present. Unknown dimension term will be present, while equating the unknown dimension will be calculated. This is the general procedure for static loading. In case of dynamic loading, if the type of the load is completely reverse load. Therefore, the induced stress will be completely reverse stress, and therefore the mean stress or average stress will be having value of 0. Therefore, the only sigma A, that is amplitude of the stress, will be of importance, and that is required to be taken into account. Hence, whenever completely reverse stress is present in the system or the machine part is subjected to completely reverse stress and expected life is of infinity, then again we have to use the same universal design equation, that is sigma induced is equated with sigma permissible, but with a certain modification. In this case, sigma induced will be calculated by usual way of the force divided by cross sectional area, or if it is a bending case, then induced stress will be given by my upon I. M is the bending moment, y is the distance of extreme fiber from the neutral axis, I is the moment of inertia. Likewise, left hand side will be same as in case of static loading, but on right hand side sigma permissible. Otherwise, in case of static loading, it is calculated as SYT or SUT divided by factor of safety. But in case of completely reverse stress, machine part is subjected to completely reverse stress and expected life is of infinity, then in such case, sigma permissible is calculated as SE upon factor of safety instead of SYT or SUT divided by factor of safety. Sigma permissible is calculated as SE upon factor of safety, where SE represents the endurance strength. It is irrespective of nature of material of the machine part, whether the nature of material of the machine part is ductile or brittle. In any case, in both cases, we have to use SE, the endurance limit for the material of which the machine part is made. So SE, the endurance strength divided by the factor of safety on the right hand side. Left hand side, sigma induced as usual in case of static loading, how we calculate sigma induced. In the similar way, we are going to calculate sigma induced in case of fluctuating load or completely reverse stress also. So while equating sigma induced with sigma permissible, there will be unknown dimension on left hand side, and that will be calculated by the usual way as in case of static load. The main difference lies in the right hand side, wherein right hand side sigma permissible, allowable or permissible stress is calculated by dividing the endurance strength with factor of safety as against SYT or SUT divided by factor of safety. So to clear the idea, let us solve one numerical where idea of designing the machine part subjected to completely reverse stress and expected life is of infinity will be clear. So this is type 1. Type 1 completely reverse stress subjected to infinite life. Type 2 completely reverse stress and finite life. Type 3 is fluctuating stress using Soderberg lines or Goodman line or Gerber line. And type 4 is fluctuating stress using modified Goodman line. So there are 4 different types of numericals, of which the very first type right now we are going to discuss, that is completely reverse stress. Machine part is subjected to completely reverse stress and expected life is of infinity. So here problem statement is as shown here. The arrangement or the machine part is also shown here. A plate made up of steel having SUT value for 40 Newton per millimeter square is hot rolled and normalized condition. It is shown in the figure. It is subjected to a completely reverse load plus minus, completely reverse load, that is plus minus 30. During the half work cycle, the load applied is plus 30 kilonewton, that means tensile 30 kilonewton, and during the remaining half work cycle the load changes its direction and it becomes compressive 30 kilonewton. So plus minus 30 kilonewton. The notch sensitivity factor Q is defined to be equal to 0.8 and expected reliability is expressed as 90%. The size factor is specified to be equal to 0.85. The factor of safety is 2 and we need to decide the thickness of the plate. Thickness of the plate not specified. Here this plate is having one hole of diameter 10 millimeters and width of the plate is 50 millimeters. Thickness is unknown. That unknown thickness value we need to calculate using this type 1 completely reverse phase infinite life of the machine part. So to start solution, keeping the our usual practice of enlisting the given data, we have now enlisted the data as specified here. SUT value is 440 Newton per millimeter square. Applied completely reverse load is plus minus 30 kilonewton, so plus minus 30,000 Newton. Notch sensitivity denoted by Q is 0.8. Expected reliability is 90%. Size factor is 0.85 and factor of safety is equal to 2. So now main concern or main difference while solving this example is on using the universal design equation sigma induced is equal to sigma permissible, but main difference lies in the right hand term sigma permissible, wherein for fluctuating load or fluctuating stress case sigma permissible is calculated as SE upon factor of safety, where SE is endurance limit for the material under question. So for calculating SE, we are going to adopt the practical approach wherein first of all endurance limit for the material of the plate SE dash will be calculated. Endurance limit for the material of the plate. Endurance limit for the plate is different than endurance limit for the material of the plate. Endurance limit for the material of the plate is SE dash, which will be given by 0.5 times SUT. 0.5 times SUT. Value of SUT is known to us. We are enlisted in the given data. It is 440. So SE dash, that is endurance limit for material of the plate, is 220 Newton per millimeter square. Now this is the endurance limit for the material of the plate, but we need to find out what is the endurance limit for the plate, and for that we have to multiply this SE dash, endurance limit for the material of the plate, SE dash, we have to multiply this SE dash by different correction factors, say Ka, Kb, Kc, Kd, Kg, Kf, etc. Generally, Ka, Kb, Kc, Kd are taken into account. So here, with the help of the given data, we are going to identify what is the value of Ka, Kb, Kc and Kd, and multiplying the Ac dash, that is 220, by these factors, we are going to find out AC, that is endurance limit for the plate. AC dash, please note that AC dash is the endurance limit for the material of the plate, whereas AC is the endurance limit or endurance strength for the plate itself. For finding out endurance limit for the plate, we need to multiply endurance limit for the plate material by these corrective factors. We have already discussed it in the previous video, wherein we have discussed RR modes, rotating beam endurance testing machine. There we have discussed these factors. We are taking into account these factors for modifying the endurance limit for the plate material, so that we will be in position to calculate endurance limit for the plate itself. Now referring the standard table, one can find out this K. K is the surface factor, surface finish factor rather, and by standard table, referring the standard table, one can find out value of Ka is equal to 0.67. Surface finish depends upon the manufacturing process, and in this particular case, manufacturing process is hot rolled machine part. So surface finish factor K for hot rolling manufacturing process machine part is 0.67. So we are going to take into account this. Students need not worry regarding these factors because generally in your examination these values of these factors will be directly given, or if not given they will specify the tables wherein you can read the value of these modification factors. Like here one table is specified from wherein you can read the value of modification factors, but generally it is not required to read them from the standard tables. Generally, in the problem statement itself, they will directly specify the values for these modification factors. In the given data itself, they have specified value of KB, the size factor, as equal to 0.85. Then expected reliability is 90%, and if expected reliability is 90%, then modification factor Kc happens to be equal to 0.897. So Kc is equal to 0.897. So only one modification factor Kd is remaining. How to find out value of Kd? That will be seen in the next slide. So here Kd modification factor for accounting the stress concentration. Kd is the modification factor for accounting the stress concentration. It cannot be read directly from the standard chart, rather it is required to be calculated. Kd is given by 1 upon Kf, reciprocal of Kf, where Kf is given by 1 plus Q times Kt minus 1. Here Q is the notch sensitivity. In the given data, always notch sensitivity Q is specified. In this particular case also they have specified a value of Q as 0.8. So this you need not worry regarding notch sensitivity Q value because it will be always be specified. And KT many times it is specified, but sometimes it is required to find out value of KT from standard chart or standard graph. As in this case, they have specified, they have shown the standard graph for value of Kt. Kt value, the theoretical stress concentration factor can be read from this standard graph. Now here you can see here value of Kt is on y-axis, whereas value of ratio dW, d upon W is on x-axis. D is the diameter of the hole on the plate and W is the width of the plate. In our case, diameter of the hole is 10 and width of the plate is 50. So D is 10, W is equal to 50. So D upon W in our case is 0.2. We can note that hole diameter is 10, width of the plate is 50. So ratio D upon W is 0.2. For 0.2, the Kt value, standard theoretical stress concentration factor for D upon W ratio is equal to 0.2 is equal to 2.5. So Kt value can be read from this graph, and it's for the particular this case value of Kt is 2.5. You can read here D upon W ratio is 0.2 and for dW is equal to 0.2, value of Kt is 2.5. Now we are having with us value of Kt 2.5, value of Q as specified in the problem statement 0.8. So using value of Q and Kt in the formula, one can calculate Kf. Kf in this particular case happens to be equal to 2.12. Reciprocal of this Kf will give you or will lead you to the value of Kd, the modification factor which will account stress concentration. Kd is the modification factor for accounting stress concentration and Kt is the theoretical stress concentration factor. Please note the difference between the two. Also note the difference between notation of the two. So Kd is the reciprocal of Ka, that is the reciprocal of 2.12. So it happens to be equal to 0.4717. Now we are having with us value of Ka, Kb, Kc, Kd, Ka 0.67, Kb 0.85, Kc 0.897, Kd right now calculated as 0.4717. So using these values, Ka, Kb, Kc, Kt, Ka is 0.67, Kb is 0.85, Kc is 0.897, Kd is 0.4717. Using these values and value of Ac dash as 220, we can calculate Ac, that is the endurance limit for the plate. And in this particular case, this AC happens to be equal to 53.01 Newton per millimeter square. Now dividing this AC by a factor of safety, we will be having with us sigma permissible or sigma allowable. Allowable or permissible stress for the case under consideration. So here factor of safety is 2, AC is 53.01. So sigma permissible happens to be equal to 26.5 Newton per millimeter square. Now you can see here, for finding out unknown dimension, that means for designing, we are going to adopt the same universal design equation wherein sigma induced is equated with sigma permissible, while equating unknown dimension will be found out. On the left hand side, sigma induced, wherein unknown dimension term will appear in left hand side, and sigma permissible right now we have calculated as AC upon factor of safety. In this particular case, sigma permissible is 26.5 Newton per millimeter square. Sigma induced is the induced stress inside the plate, which will be given by the force P, load or force P divided by cross section area. So critical cross section area will be 50 minus 10 W minus D multiplied by the thickness. Thickness of the plate is T, and at critical cross section the width will be 50 minus 10. So width at the critical cross section is W minus D 50 minus 10 multiplied by the thickness of the plate, that will represent critical cross section. Applied force divided by critical cross section. So induced sigma induced will be 750 upon T. Now we have to equate sigma induced with sigma permissible. Sigma induced is 750 upon T and sigma permissible is 26.50. So 750 upon T is equal to 750 upon T is the sigma induced. Sigma permissible is 26.5. While equating unknown dimension, the thickness will be calculated. In this particular case, the thickness happens to be equal to 28.3 millimeters. Therefore, plate thickness for safe operation for infinite life, when the plate is subjected to completely reverse, that is plus minus 30 kilonewton force, the for safe operation we need to maintain the plate thickness at least equal to 28.3 or say 29 millimeter, rounding it off to next integer value, 29 millimeters. So likewise, whenever a machine part is required to be designed, which is subjected to completely reverse loading and expected life is infinite, we need to take into account AC, that is endurance limit for that particular part, and using that, dividing it by factor of safety, we will be in position to calculate sigma permissible. When equated with sigma induced will have unknown dimension term, and that unknown dimension term will be calculated. This is first type of numerical that may appear in your SPPU examination based on this unit number 3. So in this today's video tutorial, what we have learned, we have learned how to find out different correction factors. If not directly specified in the problem statement, how to find them out. Just like we have seen how to find out KD, the modification factor for stress concentration, how to find out different correction factors if not specified in the problem statement that we have seen here. Then we have seen how to find out endurance limit for the given machine part. Endurance limit for the material of the machine part is given by 0.5 times SUT. but multiplying AC dash by different correction factors, we need to find out endurance limit for a particular machine part. How to find it out? That also we have discussed and seen in this video tutorial. Also, we have seen how to design a machine part which is subjected to completely reverse loading, and hence completely reverse stress is getting induced inside the machine part. For such cases, if expected life is of infinity, how to design that using the basic design equation, that is sigma induced is equated with sigma permissible. How to design such a machine part, that also we have discussed through this video tutorial. That's all for today's video tutorial. Thank you.